So in this problem we have two frictionless pulleys which are placed at a distance d from each other, and d is equal to 2 meters. And then there is a string wrapped around it like this, and then at the bottom we have a mass m hanging in equilibrium on this string. So we are given the total length of the string, which is 5 meters, and that's the entire length of the string. And we are also given the mass density, that is the kilogram per unit length of the string, so that's 1.00 grams per meter, so it's very small. And we know the mass, so the mass is 12 kilograms. So in part A of the question, we need to find the tension in the string if the mass is in equilibrium. Well, we can draw a free body diagram for the mass. So there is a mg force acting on it from the bottom, so this is a free body diagram. And then there are two forces from the two strings pulling at an angle. So this is tension, and then a similar force T pulling it this way, and let's say this angle is alpha. Well, by observing this free body diagram, you can see that the vertical components of the two tension forces have to balance the mg force. So what you can say is that the mg is equal to 2 times the vertical component of T. Well, from here it follows that the vertical component of T is T times cosine of alpha. T cosine of alpha. So all we need to do to calculate for tension is first find this cosine alpha. And we can do that by looking at this picture here. So we know that this total length is 2 meters, so this is 1 meter. The whole thing is 5 meters, so each of these sides is 1.5 meters. So 1.5, 1.5, and 2, that makes it 5. Well, if you look at this triangle, then you can use the Pythagorean theorem to calculate for this length. That's 1.5 square minus 1 square. And if you do the calculation, you should get 1.18 meters. Yes, that's correct. So this is 1.18 meter. So cosine of alpha would be this divided by this. So from here, then you can calculate for tension. That's mg over 2 cosine alpha. M is equal to 12 times 9.8 over 2 times cosine alpha, which is 1.18 over 1.5. Well, if you do the calculation, you should get 78.9 Newton for the tension. You may argue, well, why we don't account for the mass of the string itself if we're given the mass per unit length. And it turns out that the mass of the string in this particular example is negligible. You can calculate the total mass of the length of the string, that's mu L. So that's 1 times 10 to minus 3 times the total length, which is 5. So you just get 5.10 to minus 3 kilograms, and this is nothing compared to the mass of the block. So in principle, we can just ignore the mass of the string in this case. So that's the answer to part A. 78.9 newtons is the tension inside the string. The next part is saying what should be the frequency of a standing wave in this string such that you get a standing wave pattern that looks like this. Okay, so you get something that looks like this. So you get 3 loops in the upper part of the string. So what should be the frequency of vibrations for the given tension to get 3 loops in the standing wave. Okay, so let's try and work it out. Well, if you just look at that pattern, and let me redraw it here, that's how it looks. We know that one single loop accounts for the length of lambda over 2, so half of the wavelength. And as you can see, we have 3 halves which correspond to distance d, so we can say that d is actually 3 lambda over 2, so 3 halves. On the other hand, we know that the lambda times the frequency is equal to the velocity of the wave in the string. Well, we also know that velocity is related to tension and the mass per unit length. So this is equal to tension in the string divided by mu square root. Well, if you then substitute everything in, you can calculate for frequency. So first of all, lambda from this equation is simply 2d over 3 times F equals tension over mu. So frequency is equal to 3 over 2d tension over mu. We know the value for tension from the previous part. We know the value for mu and d. So we can just calculate that. If you put the numbers in, you should get 2.11 times 10 to the power 2 hertz for the frequency. Well, because it's a string which is fixed at both sides, and we have 3 loops in a standing wave, this mode corresponds to the third resonant frequency. So this is, you can say F3, and similarly that's lambda 3. Okay, so that's it.